Greetings from Avarta. In this video, I will try to explain natural or free convection inside a two-dimensional cavity. This problem is significant as it involves flow and heat transport and is typically used as a CFD validation test case. Well, the objective of this presentation is whether we can make a person understand the natural convection inside a 2D cavity who knows only that the hot air rises from his or her high school physics. The question is it that simple? The straight answer is no, it's not that simple, which will be clear in the coming slides. However, I will try to explain with whatever knowledge that I have related to this field without being too technical. Two-dimensional box or a cavity is shown in the figure. The thickness of the box is small compared to the other dimensions, thus making it two-dimensional. One surface, that is the left surface, is maintained at constant hot temperature and the other right surface at constant cold temperature. Now, there is no heat flow either from inside to outside of the cavity or vice versa across all other surfaces. Please note the term G, which is a gravity term that plays a significant role in natural convection. So what is natural convection or why it is called so? Natural or free convection is a heat transfer due to the motion of fluid parcel which is set naturally without any external influence due to the applied temperature difference. Hot air becomes lighter as it expands, thereby increasing the volume and decreasing its density. Hence, it rises above the denser cold air. The same way as you see why a hot air balloon rises as it experiences a buoyant upward force that pushes the balloon upwards from the surrounding denser cold air. So the whole motion inside the cavity may be set up simply by the difference in density of the air due to the applied temperature difference across left and right boundaries as shown in the figure. Now I will take some time for this slide as I find this to be important to make a person understand the modes of energy transfer when you talk about natural convection. We all know from high school that for a solid material that molecules transfer heat by intermolecular vibration or electron movement. This mode of heat transfer or heat flow is called conduction heat transfer. When you talk about this type of heat flow in bulk, the property of the material, which is air in this case, that governs how quickly the heat can flow is called the conductivity of the material. For air and for other gases, the conductivity is very low compared to solids. The material also has another property, that is to store the heat, which is called the heat capacity. When the heat starts flowing or when the transport is initiated, these two properties govern how quickly the heat flows or the heat flow rate. The ratio of thermal conductivity to the heat capacity is called the diffusivity of the material. The next thing is diffusion. So the diffusion is, as we have studied in school, is a transport process that is initiated whenever a gradient of the transport variable is present. To give an example is when you add salt to water, the water becomes salty since the salt water at high concentration diffuses to its lower concentration. In the present scenario, heat is a transport variable governed by an existing temperature gradient provided at the side walls, that is the left and right side of the cavity. Hence, the heat diffuses in the material medium. To understand the difference between conduction and diffusion, the tank and tube analogy may be recalled. Now you can imagine that several tanks are connected by tubes. The tubes are connected between the tanks, and water flows through the tubes and fill the tanks from the left to the right. You can imagine like that. In the first case, the tubes connecting the tanks are kept near to the top of the tank, and in the second case, the tubes are kept near to the bottom of the tanks. Now, it is easy to comprehend that water reaches faster to the last tank. That is, if it flows from left to right, it reaches faster in the second case. Because it does not need to fill the tank, unlike in the first case, because it is the tubes are connected at the bottom of each tank. Here the tanks represent the heat capacity of the material, and the tubes the thermal conductivity. So the heat diffuses faster for a material with large thermal conductivity and low heat capacity. So that's for the heat conduction part. Now next we talk about the other mode of heat transfer in fluids. In fluids like water and air, the molecules are free to move like in bulk. Hence the energy transfer mode in such medium is primarily in this way and is called convection, or the convection heat transfer. We know that the hot air rises because it becomes lighter or less dense than cold air, as explained in the previous slide. Now this chunk of air or air parcel carries with it the heat that it absorbed or transferred from some other medium, let's say a hot surface. Depending on several factors such as bulk or mass of air that can carry the heat away from the surface, this mode of heat transport becomes ideal for cooling a hot surface if required, such as an engine inside a car. Now, unlike the case presented here, the cooling of an automobile engine by air is through forcing the cold air to flow over the engine, which is approximately at the car velocity. Hence, a term used for such convection mode is called forced convection. The other mode of heat transfer is by radiation, which is insignificant for this case when compared to the conduction and convection heat transfer. In the present case, the medium is fluid and the modes of energy transfer are through combined action of conduction and convection. Um, the end of the simulation or experiment, you often see some results as shown here. The color contour maps show the temperature distribution. The red band shows the hottest temperature while the blue band shows the coldest temperature. The color bands from red to blue correspondingly represents the temperature range from hot to cold temperature. The lines demarcating the color bands are called isotherms, or lines in regions or space that have same temperature. Results shown here from Anupravaha, one of the first indigenous or Indian multi-purpose CFD solvers developed by IIT Kanpur, IIT Guwahati, and IIT Hyderabad for Baba Atomic Research Center. Along with the temperature profiles, the streamlines are also shown on the left. A streamline is a line where if you draw a tangent at any point, it gives the direction of velocity as shown by the arrows in the figure. Let's examine figure A. As a result of the temperature gradient, the air near to the hot surface rises and goes to the top, pushes the air, which in turn pushes the cold air at the right surface downwards. So this sets up a slow motion or at a low velocity, as shown in the figure A. In fact, if you can imagine if the convection was not set up for some reason, for this case, if the temperature difference was not that significant to set up the motion, and the heat transfer then would only be by diffusion, then the temperature profile would be parallel bands, and the isotherms would be parallel lines to the hot and cold surfaces. One reason being that the diffusion of heat is isotropic, that is direction independent, since a diffusion is characterized by a random molecular motion that has equal probability in all directions. Hence, we see that the heat flows uniformly in the direction of temperature gradient. But once the convection sets in, the chunk of air parcels transport the heat in the direction of flow, then becomes direction dependent or direction oriented, which is the reason why as the flow strengthens from A to C, figure A to C, there is a significant change in the temperature profile as more heat is transported as the result of more strength in the flow. In other words, we can classify which mode of heat transfer is more dominant based on time scales. That is, time scales for each mode, that is diffusion and convection. Uh, the time scale is nothing but the time taken for the heat to diffuse in terms of in the case of diffusion, and correspondingly the time taken for the heat to convect in the case of convection. So you can imagine and think logically that if the time taken or the time scale is more for diffusion uh, and less for convection, then the flow will be more and the heat transfer will be more convection dominant. Uh, Another thing is that by this time you would have noticed that the isotherms ends perpendicular to the top and bottom surfaces. The reason being that there is no heat flow across these two surfaces. If you recall from the definition that in order for the heat to flow, there should be a temperature gradient. And if there is no heat flow or heat transfer across the surface, the temperature gradient is zero, which means that there is no variation of the isotherms normal to the surface. So what are the factors that initiate a free convection? The first one is the temperature difference, as you have seen from the previous slides, that make the hot air to expand, become lighter and rise. This sets up an airflow naturally. The larger the temperature difference, the more is the effect of heat transfer due to convection. Next is the volume of air displaced, which in turn is connected to the temperature difference. If the applied temperature difference is significant enough to displace a larger mass of air, then that imparts more strength to the flow and more effect by convection. What about the type of fluid? Does that make any effect? Well, yes, the answer is yes. The properties of fluid, such as density, viscosity, coefficient of thermal expansion, and thermal diffusivity, all play a key role. For example, as the hot air rises and the cold air sinks, the sinking air experiences a viscous drag effect and hence can have a decelerating effect on the flow velocity. So when you replace air by water in the same cavity with the same applied temperature difference, can you predict the profiles? This is a question that I pose to you now. Will it be the same as before? Just think about it. So with that, I have come to the end of the presentation. Hope you have enjoyed the video. Please share your thoughts in the comments section, as there could be mistakes in this video and it helps me to rectify those mistakes. Last but not the least, if you like our channel, then please do like, share and subscribe for more interesting videos. Thank you.